and welcome to another episode of Tesseract Talks, the place where we put the spotlight on new technology trends. I'm your host, Marko Rukavina, the founder and CEO of Tesseract Analytics. Today's episode focuses on the topic that is becoming mission critical across energy, manufacturing, utilities, and critical infrastructure. How to enable operational technology while protecting cyber-physical systems from increasingly sophisticated threats. We will be discussing industrial cybersecurity, OT risk, and why traditional IT security approaches often fail in cyber-physical environments. Joining me is Andrew Ginter, VP of Industrial Security at Waterfall Security Solutions. Andrew is widely recognized as one of the leading experts in industrial and OT security, working closely with asset owners and operators around the world. Andrew, welcome to Tesseract Talks. How are you?
I'm very well. Thank you for having me, Marko.
Great. Well, to start off, can you briefly tell us about your background and how you ended up focusing on industrial security?
Sure. I mean, it's been a long time. As a young man, I bounced around. The grass was always greener. And then I wound up settling in because this was the opportunity in Calgary where I live. I settled into developing control system product at Hewlett-Packard. We were automating the world's largest pipelines. We were automating entire power grids with technology that is widely used today. And moved from there to Agilent Technologies, where the thing to do in the mid 1990s was to connect IT and OT networks. And the product was middleware. So I developed middleware products connecting a lot of IT and OT networks, contributing to the cybersecurity problems that now plague many industries. I got religion in a sense. I wound up the chief technology officer at Industrial Defender, developing the world's first industrial SEM, security information and event management system. And now the last 15 years, I'm at Waterfall. I have the opportunity to work with the world's most secure industrial sites, learn from them, and, share the knowledge. I've written 3 books on the topic. So that's how I got here.
Amazing journey so far. You've spent much of your career focused on industrial and OT security. What drew you in this domain specifically, and what makes securing cyber physical systems fundamentally different from securing traditional IT environments?
Well, it's very confusing. The space, there's a lot of computers in IT networks. There's a lot of the same computers in OT networks. And then there's a bunch of special stuff in OT networks. A lot has been written about the difference between IT and OT. A lot of that writing is mistaken. It focuses on the symptoms of the difference, not the root cause. The root cause is consequence. What is the very worst that can happen on most business networks? You leak 100,000 people's personally identifiable information into the internet. Your systems are encrypted. You have to restore from backups. You have to buy identity fraud insurance for 100,000 people. The whole fiasco costs you $22 million. What's the very worst that can happen on a power plant automation network or a passenger rail switching system? The rails switch incorrectly. High-speed trains collide. Hundreds of people die. Mass casualty event. This is the essential difference between IT and OT. You cannot restore human lives nor damaged equipment from backups. A second fundamental difference that a lot of people get wrong is the difference between espionage and sabotage. On IT networks, most of the time, information is the asset. We want to prevent theft of personally identifiable and other valuable information. We need to protect the information. On OT networks, usually information is not the asset we're protecting. We're protecting human lives. We're protecting the environment. We are assuring safe, reliable, and efficient physical operations. We're preventing sabotage, not espionage. And if you go back 50 years and look at the theory, or do your theoretical homework, a seminal paper by Bell and Lapadula talked about how to prevent espionage. There's a theory of how to prevent espionage. Biba, 2 years later, produced a different theory, how to prevent sabotage. The difference is consequence, and the difference is preventing sabotage, not espionage. You use a lot of the same tools. You have a lot of the same computers, but you have to manage them differently.
As we look across industries like energy, manufacturing, water, and utilities, what are the biggest trends and security challenges you are seeing today in OT and industrial environments?
Biggest trend is 50 years old. For 50 years, we have been automating physical operations to make them more efficient. This is why we have cheap cell phones. This is why we have cheap drinking water, because we've automated everything. And all modern automation involves computers. For 50 years, we've been deploying more and more computers into our automation systems. We've been deploying more and more targets for cyber attacks. And in the modern world, data in motion is the lifeblood of automation. For 50 years, we've been connecting those increasing number of targets increasingly. And again, Biba's theory of cyber sabotage, by definition, all cyber sabotage is information. The only way a control system can change from a normal state to a compromised state is if attack information enters it. And so for 50 years, and if I may, all information flows, you can prove mathematically that all information flows can, in theory, encode attack information. And so for 50 years, we've been deploying more and more cyber attacks. We've been more and more computers, targets for cyber attacks. We've been connecting those computers, creating an ever increasing number of opportunities for attack information to enter those targets. That's the world we live in. I'm asking you, are either of those trends disappearing in the next 20 or 30 years? I don't think so.
Yeah,
the cybersecurity problem is going to get much worse before it gets any better. The other trend we see is that after 20 years of this, the OT security initiative really started in earnest about 20 years ago. Governments all over the world are putting out regulations for critical infrastructures, for other systems. Standards have emerged. The trend is more and more people recognizing how much trouble we're in and demanding that we do something.
Many organizations still try to apply traditional IT security tools and architectures to OT environments. From your perspective, where do these approaches break down when applied to cyber physical systems?
Well, let me start with, it's not surprising that people do this. Back of the envelope calculations suggest that in the world, there's maybe 50 times as many IT security experts in existence as there are OT security experts. And so when you need expertise, who do you call? A lot of the time you pull IT people over into OT. And so there's constant leakage of the IT perspective into OT. The battle between the perspective of IT, protect the information, the confidentiality, integrity, availability of information. That perspective is in constant conflict with the assure, safe, reliable operation. So leakage is a thing. Imagine the engineering community has figured out how to build bridges at 1/3 of today's cost. Carbon fiber, something like this. Now, I've got gray hair. I've seen the video. Anyone who hasn't seen the video of the Tacoma Narrows Bridge disaster should watch it. The engineers of the day, this was 1940, almost a century ago, had not figured out the concept of harmonic frequencies. A stiff bridge came up on this very long suspension bridge, started it oscillating, and it tore itself apart. Imagine that the new design, 1/3 of today's cost, is riddled with harmonic frequencies. People walking across the bridge start the wretched thing vibrating. And so the engineers have designed active dampers, multiply redundant hydraulics, multiply redundant power supplies, multiply redundant control systems, and AI controls the whole thing. The bridge feels rock solid because of these dampers. How happy would you be driving across that bridge every day if you knew that the design engineer hoped that if we detected it in time, we could scramble an incident response team fast enough to prevent disaster? Hope is not what we expect of the engineering community. We expect bridges to be designed to carry a specified load in a specified operating environment for a specified number of decades with a large margin for error. That's the expectation for an engineered artifact where public safety is at risk. I'm not saying don't do detect, respond, and recover. Detect, respond, and recover is part of industrial cybersecurity, but preventing disaster has to be the top priority. It's not a difference. Again, the difference between Biba and Bell LaPadula is not technology. It's perspective. It's focus.
Okay. And this brings us to Waterfall Security. How does your approach to cyber physical protection differ from more conventional OT security strategies? And why is that distinction important?
Again, when we're talking about safety, when we're talking about $1 billion plant suffering an unplanned shutdown and costing us $250 million over the course of a couple of weeks. This happened a month ago or a couple of months ago at Jaguar Land Rover. Suffered $1 billion in direct damages and estimating a couple of $1 billion of damages to the UK economy. When we have really bad stuff that can happen, we need, again, deterministic protection. We expect that those consequences, to the greatest extent feasible, are impossible, not just reduced probability, are practically impossible. And so what Waterfall produces is a technology that solves one piece of the puzzle. We don't claim to solve the whole problem. You deploy our stuff. It's called a unidirectional gateway. We have a whole family of products, but they're all based on the concept of the gateway, which is a piece of hardware that sits usually at the connection, at the consequence boundary, the connection between two networks with dramatically different worst case consequences, the IT network and the OT network most often. At that IT-OT boundary, the technology replaces a firewall. The hardware part of the technology is physically able to send information in only one direction. Think engineering grade. There's a two circuit boards. There's a laser in one board. There's a receiver in the other. There's a short piece of fiber in between. You can physically send information from one circuit board to the other. It's not physically possible to send anything back. There is no laser in the receiving circuit board. This is engineering grade unidirectionality. It does not matter how sophisticated the attack is. You can't change a photocell into a laser. You can't, if you could transmute matter at a distance, you would change lead into gold. You wouldn't bother with cyber attacks. And so we can send information from the OT network out to the IT network where we can profit from access to the OT information without any cyber attack information leaking back. And that's the hardware. There's also software involved. The software makes copies of servers so that when you need the data on the IT network, you connect to exactly the same kinds of servers as you normally would have connected to on the OT network. Everything that used to work still works. So the hardware gives you engineering grade unidirectional security. Information can flow out and no attack information can get back. And the software makes everything compatible, convenient, so that anyone on the IT network who needs the data connects to the same kind of server as they would normally have to pull the data. They don't see a difference in terms of the behavior of their systems or their users.
Can you share a concrete customer example or a case study where this approach made a measurable difference, either in reducing risk or enabling new operational capabilities safe?
Absolutely. So, this is cybersecurity. A lot of our customers don't like us using their names, but one of our customers has, I live in the city of Calgary, Alberta, Canada, 1.3 million people. City of Calgary water system uses our stuff, and they've talked about it in public. They've given us permission to use their name. The scenario where they got started with the technology was this. This was the wastewater treatment for, again, 1.3 million people. Researchers at the University of Calgary up the road wanted to, they were doing work on residual pharmaceuticals because the wastewater is released back into the ecosystem. And if there are trace amounts of medicines that survive the treatment process, downstream communities consume those medicines. And this is not good. This is a well-known problem in the field. The researchers were trying out different ways. The government of Alberta said this is important research and ordered the city of Calgary to support the research by sending real-time data from the water treatment system into the researchers' systems at the university, connecting the OT network to the university network. And the city of Calgary said, no, thank you. Waterfall, come in here. And they had some spare Pi licenses. Pi is the dominant process historian vendor. Aviva Pi. They think of it as a relational database on steroids, optimized for real-time time sequence data. They had a Pi license where they had a Pi system where all of the data was. They had an extra license they donated to the university. They put the gateway at the connection between the OT network and the internet over to the university, and they made a copy of the Pi system out of the OT system into the university. And now in the university, the researchers could access their Pi system with all of the OT data in it, and nothing could leak back through the hardware into the OT network. So that was them getting started with this. And it's a concrete example. The connection between the internet and the OT network is a consequence boundary. That's where you use this class of protection to prevent attack information from the internet leaking back into physical operations.
Great example. And looking ahead as industrial environments become more digital, automated, and connected, how do you see the OT security landscape evolving, and where is Waterfall focusing its innovation next?
Again, the mega trends are not diminishing. I was talking to people in the industrial world. They had 5 or 6 plants. One of their plants, I won't go into detail, the automation system for, let's say it's a power plant, a generating unit. A power plant might have 5 or 6 generating units, a large one. Each of them is sort of self-contained and produces power. The automation in a generating unit, older stuff, there was maybe 1,000 or 2,000 CPUs in the automation system for that unit. They said they had expanded the plant. They built a new generating unit. It had closer to 50,000 CPUs in the automation system. The mega trend, increasing numbers of CPUs, increasing connectivity, are not reversing. And we have to deal with that. Everybody needs to connect these systems to the cloud. They need to connect these systems to the internet. And so a big deal, especially since COVID, is remote access. So Waterfall's contribution to the field in the last year or two is hardware enforced remote access, not just software, where if you find an exploit, if you find a zero day is a defect in a piece of software that you can take advantage of that nobody else knows about yet, that there is no security update for. The bad guys can use this with impunity. Even if you find a zero day in the remote access system, it doesn't help you because you've got hardware protecting you, not just software. So this is Waterfall's latest contribution, hardware enforced remote access. Heavy industry is responding. They're saying, whoa, something new in the world. We're worried about people taking advantage of software. We need hardware enforced protection. Here we go. In fact, in the last 12 months, 2 different government documents have come out, guidance from, multiple governments. We're talking CISA in America. We're talking the UK NCSC. We're talking the Canadian CCCS, all undersigned these documents saying, yes, please use hardware enforced solutions, especially for the dangerous remote access function where you're connecting your OT network to the internet. So that's the latest, is these risk is not going to go away. We need to invent new stuff to address the risk. And when the consequences are unacceptable, we need deterministic engineering grade solutions.
That will be following closely the trends and as well what Waterfall will be focusing on. Thank you so much, Andrew, for sharing your valuable insights on enabling OT through cyber physical protection. I hope to see you again in future on another episode of Tesseract Talks, or perhaps in person on some security event.
Well, thank you so much for having me. And, thank you to the listeners for their interest. And I hope this has been useful.
Great. Thank you for tuning in. And until next episode, bye.